So, as Pat astutely noticed, we are back to matrices. So the reason we are moving back to matrices and kind of the reason behind that seemingly weird order is we started off the beginning of the semester talking about analytical solutions to differential equations, right? How can I find the actual function y that is this differential equation, that solves this differential equation? That was like the first, most of the semester. Then we moved into numerical solutions. So what were we doing with numerical solutions?
Trying to approximate the answer.
Yeah, trying to approximate the answer. So that was Euler's, improved Euler's, the Adams methods, all those stuff that you were coding, right? So what we are going to move in today is qualitative solutions. So in other words, like how can we describe or understand the behavior of the solution? So we're not actually interested in getting a function. We're not even actually interested in numerically approximating it. We just want to like describe what is happening with this solution. So we do this a lot by looking at graphs, and we've actually done a little bit of qualitative analysis already this semester with matrices. So that's what we're going to do today. We're going to review that before we get into new stuff. Okay. So we're first going to review what we know about linear systems of ODEs. And so we had an equation, x prime equals a x, where a was a matrix and x was a vector. So we mostly looked at a being a 2 by 2 matrix, and we're going to continue that because it's easy to graph and look at. If I wanted to expand this and write this as like a system of equations, well, I guess it is a system of equations. If I wanted to write it as like 2 equations instead of condensed in this matrix vector form, how would I do it? Yeah.
A11, you just go across the top of the matrix and then the bottom of the matrix.
So let's expand this a little bit. This would be x1, x2. Then we'd have a11, a12, a21, a22. Oh, and both of these are prime on the left-hand side times x1, x2. Okay. So vector is just a one-dimensional matrix, and it's where we normally end up storing these values. Okay. And then if I wanted to write this out, I could say x1 prime equals, and then I could do my first row dotted with my vector, right? So I've got a11 x1 plus a12 x2. Can someone give me x2 prime?
A21 x1 plus a22 x2.
Perfect. Right, so what's important about these systems is they depend on one another, right? X1 prime depends on both x1 and x2, and x2 prime depends on x1 and x2 as well. Okay. Does anybody remember what the equilibrium value of this system was?
0.
Yeah, 0 vector. So our equilibrium vector was the 0 vector. Why? Why? Because if this is not if it is invertible, now I have to think through. It's a great question.
Unless it's just something that we should know, like that's fine.
It is something we should know, but it has a reason. So let me, if I wrote it down in my notes this time.
you plug in zeros, the primes are also going to be zeros. So that means if you start at 0, 0, you can't go anywhere.
Yeah. That's a great way to think about it. So if I plug in zeros, my primes are going to be 0, so you can't go anywhere. That's a perfect way to think about it. Still not convinced?
I mean, sure, I'll believe it. I mean, I see that, but it's fine.
Okay. Another way we can think about it is if I had the primes as zeros and I tried to graph these, they both go through the origin, and then the only way for them to intersect is through the origin. I think it's a good way to think about it. So let's do that. So if I replaced my primes with zeros, so 0, 0 equals a11 x1 plus a12 x2, a21 x1 plus a22 x2. Okay. If I attempted to graph this on an x1, x2 coordinate system, what is your x2 intercept? If I solve my first equation for x2, what am I going to get? Rob?
0, 12.
Well, if I solved it for x2, I would get negative a11 over a12 x1, right? By subtracting a11 x1 to the other side and then dividing everything by a12. So my x2 intercept is 0, or my y-intercept is 0, right? And then if I do the same thing over here, I'm going to have x2 equals negative a21 x1 over a22. So these are both lines, and the only place they are going to intersect is the origin, because they both have a x2 intercept of 0. Have I convinced you, Sarah?
Yeah.
Okay. No, that's fine. It was a great question. I should have known the answer to that. So when we were talking about this equilibrium value, what are some things we used to discuss it?
Classification.
Yeah, we classified it. So do you remember how we classified it? Anybody? I know it was a long time ago.
Values.
Yep, we found the eigenvalues, and then we discussed how the eigenvalues affect the equilibrium value. So we're going to summarize what we spent like 2 weeks learning. Okay. So we are going to have our eigenvalues. Then we are going to have our type of critical value or equilibrium value, and then we are going to talk about its stability. So for our first section, we're going to focus on real eigenvalues, and then we'll get into our complex eigenvalues. So like our first, like 2 things we could have is we could have 2 positive reals, or we could have 2 negative reals, right? So do you remember when we did our phase portrait, what that looks like for those 2 cases?
Diverging and converging.
Diverging and converging. Okay, good. So it either went away from 0, 0, or it went towards 0, 0, right? So since it's either leaving 0, 0 or going towards 0, 0, we call this type of critical point a node. Does anybody remember if the two positive reals were going away or towards 0, 0? Away. Great. So its stability here is unstable. And then the two negative reals were going towards it. So what vocab word did we use?
Stable.
Stable. Exactly. We're going to get even a little bit more granular now. And instead of just calling it stable, we're going to call it asymptotically stable. So the reason we are going to call it asymptotically stable is the following. So when I do a phase portrait, what are my axes?
X1 and X2.
X1 and X2. Perfect. So if it is asymptotically stable, then all my trajectories are going to be moving towards 0, 0, right? But if instead I was to do a graph where I had T on the horizontal axis and X1 on my vertical axis, and then a second graph where I had T on my horizontal and X2 on my vertical, right? So in this case, I'm graphing my solutions over time. Because I think something we forget about these, we do have this underlying time factor, right? Because X1 and X2 are themselves equations with independent variables. So if I was to graph these, a bunch of solutions, I would have things that are going towards 0, 0, but they're never actually going to touch them. So they have y or x1 equals 0 as an asymptote. So same thing over here. So that's why we're going to call it asymptotically stable, because it is approaching 0, but never actually reaching 0. What would be like the one exception to it reaching 0?
It starts at 0.
If it starts at 0. If it starts at 0, it's not going to go away from 0. It's already there, right? Because that's what an equilibrium point means. It means if you start at 0, you stay at 0. Okay? Perfect. Then we could also have one positive and one negative. If we have one positive and one negative, we're going to call this equilibrium value a saddle point. And it's going to be unstable. Okay, so for our saddle points, what this is going to look like is through the origin, we're going to have our eigenvectors. And then if we were to draw our trajectories, we would get one of these situations. That does not look like an arrow, right? Where we are going to approach, but we are never actually going to reach. And then we'd have it on this side as well. So Any ideas why we call this a saddle point? It looks like a saddle in topography. So if you had in 3 dimensions a saddle point, like a Pringles chip, right? If we were to take the level curves, so if we were to like slice that Pringles chip up and be like, when I do my slices, what does that look like down on 2 dimensions? You get this shape. So it's related to that 3-dimensional shape that we have. Okay? All right. What other real combinations am I missing? Repeated, exactly. So you can have one positive real repeated or one negative real repeated. These are both going to be nodes, right? And we call it node because we can think of it as like a sink or a source. Are you going towards it or are you going away from it? And then your one positive real is also going to be unstable. You're moving away. And your one negative real is going to be asymptotically stable as well. All right. And then now we need to talk about complex eigenvalues. Are you guys okay if I erase the real part?
This is recorded, right?
This is recorded.
Perfect.
On the chart. So now we're going to have complex, where we look at lambda plus or minus I mu. Does anyone remember what part of the eigenvalue we look at to classify our equilibrium value for complex eigenvalues? The real part. So our real part can be positive, it can be negative, and it can be 0. What was special about our equilibrium value, or what was special about the graph? Yeah, it's spiral. So instead of just calling it a node, we actually call it a spiral point. Positive real, unstable or asymptotically stable? Unstable. And then we've got, for our negative real, we've got asymptotically stable. And lastly, what was special about lambda equals 0? Exactly. In our phase portrait for lambda equals 0, all our trajectories would be either a circle or an oval, right? But they're going to come back on themselves and loop back on themselves. So we call this one a center, and then this one just gets the label stable. We don't like give it that extra qualification of asymptotically stable. All right. Questions about that? So on your in-class assignment number 1, there's a couple things you could do. We're mostly working on classifying. Last night I emailed out a Mathematica file. Yes? Okay. You can use that to help you look at those phase portraits and just get a refresher for what do these look like. You just are going to have to change the A matrix.